Hello, in this session, we evaluate the varied forms of structural isomers. To begin with, we say that structural isomers differ in respect to arrangement of carbon atoms in a molecule. Let us look at the typical examples of structural isomerism. First, there are three forms of structural isomerism, namely chain isomers, two positional isomers, and three functional group isomers. The first one, the chain isomers, will differ in respect to the arrangement of carbon atoms. For example, when we represent the isomers of pentane, we will proceed and say that pentane could be a chain of 5 carbons in a row, or a broken chain in which one carbon hangs, and still a balanced chain in which 2 carbons hang in the middle tertiary carbon. In this respect, when the structure is completed, we find that we have 3 distinct structural forms of the same molecule, and this will represent structural isomers of pentane. Let me complete this using the carbon rule. Says each carbon has a maximum of 4 bonds around it, no more and no less. In this respect, each species has its own unique appearance, and the displayed structural formulae are different with respect to the arrangement of carbon atoms. So as you can see, and as I mark the borders separating each of them, the first species has 5 carbons in a row, we call it pentane. The second species has 4 carbons in a row with a methyl molecule in position 2, namely hanging on the second carbon. So we name it as 2-methyl, that's methyl in position 2, butane, because it has 4 carbons in a row. The third species has 2 methyl molecules. Each methyl is on the second carbon, so we call it 2,2-dimethyl propane, because it has 3 carbons in a row. In a nutshell, therefore, pentane exists in 3 structural isomeric forms as pentane, as 2-methyl-butane, and as 2,2-dimethyl propane. Remember, chain isomers differ in respect to arrangement of atoms of carbon in the chain. Next, we have positional isomers, which is the second form of structural isomerism. The positional isomers will differ in respect to position of the functional group. I'm going to use the alkenes and alkanols to illustrate this. To begin with, we have butene. Butene is an alkene of the formula C4H8, so we can assume that the first or principal structure form will be a chain of 4 carbons with a single double bond after the first carbon. When, however, the position of the functional group changes from the first carbon to the second carbon, we form 2 distinct structures. Let us see how this looks like. So, in completion, by the carbon rule, we have that structure, and the second structure following the same carbon rule. In conformation, each carbon has 4 carbons. Each species has 4 carbons and 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Again, 1, 2, 3, 4, 5, 6, 7, 8. Now that shows they are the same molecular formula but different structural arrangement. The border is there. So the distinction is the position of the carbon double bond. On the first case, it's after the first carbon. In the second case, it's after the second carbon. So the principal names are but 1 in and but 2 in, respectively. That shows clearly that we can form 2 distinct positional isomers from the same molecular formula of butene. The second example of positional isomerism is on alkanols. And we want to use the example of pentanol, which has 5 carbons, and we will represent it logically as 5 carbons in a row, where the OH or the functional group is on the first carbon, or simply changing the position of the functional group will also give us 1, 2, 3, 4, 5 with the OH in the position of the second carbon, or thirdly, where the OH is on the position of the third carbon. So looking at it and completing the structure by the carbon rule, this is what we have. The first species as the OH on the first carbon, we could call it pentan-1-ol. The second species, as you can see me completing there, has the OH group on the second carbon. And if you're logically following, your guess will be right. Its name will be in respect to that position, which is pentan-2-ol. The third species, in the same breath, following the carbon rule and logically assuming the nomenclature, the name will correspond to the position of the OH group, which in this case is position 3, so we could name it pentan-3-ol. In conclusion, therefore, we can say that pentanol can exist in 3 isomeric forms as pentan-1-ol, pentan-2-ol, and pentan-3-ol. Remember, these are positional isomers which differ in respect to the position of the functional group. Next, and the third form of structural isomerism is the functional group isomers. Now, we have a molecule of the form C2H6O. When we intend to represent this, we could simply start by placing the 2 carbons in a row and then affixing an alkanol species, and then completing the structure by the carbon rule and affixing hydrogens, maintaining that the number of carbons are the same, hydrogens equal, and oxygen. Counting, we have 2 carbons, we have 1, 2, 3, 4, 5, 6 hydrogen and 1 oxygen, which makes that molecule what we call ethan-1-ol, or simply ethanol, because there are only 2 principal carbons. The second case will be we have the O in between 2 carbons, and following the carbon rule, what we have is the structural arrangement in which it is displayed with 2 methyl species, so we could call it dimethyl. Dimethyl to mean there are 2 methyl molecules, ether to mean it's a family of ether. So you see here clearly that even though we have the same molecular formula, we have 2 distinct structures, each carrying 2 carbons, 6 hydrogens, and 1 oxygen. Now, the distinct arrangement has given us 2 different families. One is an alkanol, the other one is an ether, or in another way we could describe it as an alkyl. In this case, there are 2 families but with the same molecular formula, so they are functional group isomers because they differ in respect to the nature of the functional group. In summary, therefore, what have we said? We have said that structural isomerism is the existence of different structures of the same molecule which differ in respect to the arrangement of carbon atoms. We have also agreed and said that structural isomerism are of 3 main forms. The first and principal one is the structural isomerism, which is the chain isomer, which is the arrangement of carbons in diverse differing positions. The second form of structural isomers, we have said, are the positional isomers, which in this case differ in respect to position of the functional group, be it a double bond, a triple bond, or an OH, which represents alkyl. And the third form of structural isomerism, we have said, is the functional group isomerism, which differs in respect to the family formed by the arrangement of Thank you. Next, we are going to look at the second form of isomerism, which is stereoisomerism.